In the last section of the book, we looked at some basic results on infinite series, and we had some tests for when a series converges and when it doesn't. In this section, we get very serious, and we'll have a whole bunch of convergence and divergence tests that apply to non-negative series, series in which none of the terms are negative. They're all the terms in your series are greater than or equal to 0. There's a fundamental reason why those are easier to deal with that I'll say quickly at the start. But I should say that in the book, a lot of the results are stated. There are a great number of technical results stated. As I've said before, in a way, all of these results on infinite series are technical. But they're kind of absurdly technical in the book, or not absurdly, but extremely technical, and I'm going to omit some of the more technical results on subsequences, and I give kind of, in the book, I kind of give optimal statements of the ratio test and the root test, and what I talk about is going to be how they're usually used, what's usually called the ratio test and the root test without the extra part of the statement. So understand, if you're reading the section, that there are a lot of more technical statements that are not going to be covered in this lecture, but that's frequently the case. For instance, I rarely prove things in these lectures, but the proofs are always in the book. All right, a non-negative series. It is what I said. You have an infinite series, so a non-negative series. You've got some infinite series starting at some initial index m, and it's just all the bk's are greater than or equal to 0. It may be, I don't know, somewhat mystifying to you initially why these would be any easier to deal with than series in which you allow positive and negative terms. What I should say first is that we could also deal with non-positive series. The case where all the bk's are less than or equal to 0 would be just as easy as this case. In fact, you can deal with that case by negating this case and just negating all the partial sums and the limits. But if you want to pick one that you're going to prove a bunch of theorems about, you know it applies to the other case by negating. We typically pick the non-negative case and know that all the analogous results are true in the non-positive case. Why would non-negative series be easier to deal with than series that involve both positive and negative terms, though? It's for one fundamental reason. If you have a non-negative series and you look at the partial sums look like this. And so you start at b sub m and you add some terms. And what happens? So here are your partial sums. As n gets bigger, well, you add more terms. So for instance, when you go to the next partial sum, you would add another term. But all the terms are non-negative. So every time you go to another partial sum, what you've added is greater than or equal to 0. But that means that the partial sums are an increasing sequence. I mean, maybe b sub n plus 1 is 0, so we didn't change it. But if it's not 0, it went up. So the partial sums of a non-negative series are an increasing sequence. But increasing sequences have an important property that we looked at back when in the section on sequences. If a sequence is increasing, there are only two choices. Either it's bounded above, so all the SNs are less than or equal to some number, capital M, so that the sequence is bounded above, and then the sequence converges. It's one of the defining properties of the real numbers. It would converge to the least upper bound. Or the sequence is not bounded above, and that means that the sequence goes to positive infinity since it's increasing. So, form an increasing sequence. So the theorem is a non-negative series converges if and only if the partial sums are bounded above. If M is an upper bound on the partial sums, then the series converges to the sum of the convergent series. Is less than or equal to M. And another part of this theorem is if the series diverges, it diverges to positive infinity. That is, the partial sums become unboundedly large if you go out far enough. The series diverges to positive infinity. All right. This is at the heart of why non-negative series are easier to deal with than series with both positive and negative terms. A non-negative series converges if and only if the partial sums are bounded above. If the partial sums are bounded above by M, then the series converges, and it converges to something less than or equal to M. And part of that statement is if the series diverges, there's only one way for a non-negative series to diverge. The partial sums can't oscillate. They can't do anything bizarre. The only way a non-negative series can diverge is to positive infinity. Okay. Before I give a new test for convergence, I do want to mention one technical result. I said I didn't want to cover too many of the incredibly technical results in this section, but I want to be able to contrast this non-negative series with series later when we allow both positive and negative terms. And the theorem I want to state now, I'll state it roughly, it's stated precisely in the book. The theorem that I'm going to state now is just not true if you allow both positive and negative terms, and it's a little shocking that it's not true in general. So let me write a convergent non-negative series on the board. So right now we don't know many convergent series, but certainly geometric series are convergent. So let's look at the sum. The sum as k goes from 0 to infinity of, well, I don't really care, 1 over 2 to the k. So this is 1 plus a half plus a fourth plus an eighth plus a 16th, and so on. All right, we write this the way we write a finite sum, except we put some dot dot dots at the end, or we use the summation notation. But we think of it as a sum, and we're so used to adding that it doesn't even occur to us that we're just assuming associativity of addition, that you can put in parentheses here and do some of the additions first and some later and it doesn't change anything. And we're assuming commutativity of addition so that if you switch two of these, it doesn't change the sum either. So I just want to say kind of informally that for non-negative series, regrouping the terms, or grouping or regrouping the terms, so putting in some parentheses, grouping the terms, or rearranging the terms, so moving the terms around in the series, regrouping the terms or rearranging the terms. Does not affect convergence, divergence, or what it converges to. So that's part of affecting. So that, yeah, it's, if you think of an infinite series as really, here are a bunch of numbers and we're summing them, then it shouldn't matter which order you take them in and how you group them. You should always get the same thing. The theorems tell you that for non-negative series. Strangely, if you allow both positive and negative terms, there are times when you can rearrange and change you can take a convergent series and make it diverge. You can make it converge to any number. By rearranging, you can make it converge to anything you want. We'll talk about that in the next section, but the point right now is for non-negative series and at the same time for non-positive series where everything is less than or equal to 0, rearranging things and grouping things doesn't affect things at all. This is really like you've got a bunch of things and you're adding them together and you don't need to worry about the order in which you add them. All right. Still, that doesn't help us. That really doesn't help us much in deciding whether a series converges or not, unless we had another series that we knew converged already and we got the other one by rearranging or something. So a real test that's important is this test is it uses what we know about integrals to tell us about infinite series. So this theorem is called the integral test. So you start with a function. Suppose f of x, we're going to use it to define a sequence, and we want it, a series, and we want it to be a non-negative series, so we're going to require f of x to be greater than or equal to 0. Suppose f of x is greater than or equal to 0 and continuous. For x greater than or equal to some m. And suppose f is decreasing. So as x gets bigger, f of x gets smaller. Then the series, the sum as k goes from m to infinity of f of x, converges if and only if the integral from m to infinity converges. What is this? I should put a k here. Right, we take the sequence of terms that we get by plugging k into f. Here we should have this, if and only if this converges. This is not particularly difficult to show when you remember that for non-negative series, a non-negative series converges if and only if the partial sums are bounded above. What you do is you kind of compare, or not kind of, you compare, I'm just drawing a graph. Suppose the graph of f of x looks like this. So greater than or equal to 0, decreasing. Then what happens? Well, suppose you want to compare this with the sequence. So put 1 here. I'll start at 1, 2, 3, 4, and so on. If you draw in the right rectangles to represent the partial sums, we would like to know, for instance, if the integral converges, the series converges. Well, then what we'd like to do is consider these inscribed rectangles. And if the integral converges, then the area under the curve is finite. But these rectangles are inscribed, which means the sum of their areas is bounded above by the integral. But the sum of the areas of these rectangles is this infinite series, except we've omitted f at 1, or if m were 1, we would have omitted f at 1, so you have to add that extra rectangle to get this sum, but the infinite sum converges if and only if you can leave off the first finite number of terms. So this converges if and only if it converges after you leave off the first term. But that series is bounded above, the partial sums are bounded above by this integral. And so if the integral converges, this converges. The other way, you use the circumscribed rectangles. You could, by considering these rectangles, you can see that if the sums of the areas of those rectangles are this infinite series, or the sum of this series, so if it converges, then the area under this curve is bounded by this sum, and for the same type of reason that in the reals, in the real numbers, if you've got something increasing, like the area would be as this upper index approaches infinity, then it converges if and only if it's bounded above. And so if this converges, this will converge. This is the integral test. It immediately allows us to conclude things that one of which we have concluded before, but one that we haven't concluded before. So as an example, well, let's look at the harmonic series. Now, we know the harmonic series diverges. We showed it, but we used a very special argument that said, where we group things and compared with powers of 1 over powers of 2. But now it's easy from the integral test. This series converges, so we know this diverges. It's the harmonic series, we know it diverges. But I just want to show you how easy it is to conclude that from the integral test. It's, you let f of x equal 1 over x, for x greater than or equal to 1. Well, this is certainly greater than or equal to 0 and decreasing. So the integral test tells us that this converges if and only if this converges. Oh, but we know the integral of 1 over x dx. It's the natural log of, well, absolute value of x, but our x's are positive, from 1 to infinity, which means, well, really we're supposed to take, what does this infinite limit mean, this infinite integral mean? It's an improper integral. It really means the limit as b approaches infinity of this. So this is the limit as b approaches infinity of the natural log of b minus the natural log of 1. Of course, the natural log of 1 is 0. And as b goes to infinity, the natural log of b goes to infinity. So this integral diverges, and the integral test then tells us that, yes, this infinite series diverges by the integral test. Okay, but we knew that the harmonic series diverged. This isn't anything new. But hey, what if we put squares here? So then you'd have squared, squared, squared. And we want to look at that. Well, then we would want to look at 1 over x squared. Again, this is certainly greater than or equal to 0 and decreasing. So it's all a question of what does this integral do? This integral from 1 to infinity. Well, this is x to the minus 2. So this time we get x to the minus 2. Use the power rule. You add 1 to the exponent. You divide by the new exponent. You evaluate from 1 to b. So we get the limit as b approaches infinity of, what do you get when you plug in b? We get b to the minus 1 over minus 1. Minus what you get at 1, so that's minus minus, so that's plus 1. And as b goes to infinity, this is 1 over b. This part goes to 0, and you're left with 1. In particular, it converges, which means this converges by the integral test. And if you look at the theorem in the book, because we had the partial sums trapped by the integral, this actually gives you an upper bound. You can get an upper bound on what this converges to, but it doesn't tell you what it converges to. But it can give you an upper bound. In fact, it's known through complicated methods that this converges to pi squared over 6. That is absolutely not supposed to be obvious. All right. How else could you use the integral test? Let's just do one more. Let's look at 1 over k times the natural log of k squared. So 1 over k times the natural log of k squared. We don't want to start indexing at 1 because this would be 0 there, so let's start at 2. This series doesn't have a name. I'm not even going to write out the terms, but can you decide what this does? Well, for x greater than or equal to 2, you look at x times the natural log of x squared. Again, this is greater than or equal to 0, and it definitely decreases because the denominator is an increasing function of x, because ln of x is increasing, x is increasing. And so the convergence or divergence of this is equivalent to the convergence or divergence of this. Well, now you have a harder integral, but can you do it? Yeah, you make the substitution. If you haven't forgotten substitutions, you let u be ln of x. Hopefully that would occur to you fairly quickly. So that du is 1 over x dx. And we get the limit as b approaches infinity. All right, I am going to leave my limits of integration. Well, no, I won't. I'll switch the limits of integration. All right, the 1 over ln of x squared is 1 over u squared. So you get the 1 over u squared. The 1 over x dx is du. And when x is 1, u is the ln of 1, so that's 0. Yes, well, we started at 2. Yes, that's true. It would be bad to start this at 0, but we're supposed to start at 2. So let's do this. So from 2, and when x is b, u is the natural log of b. What's important here is that as b goes to infinity, the natural log of b goes to infinity. So this is just the integral from 2 to infinity of 1 over u squared du. You get the limit as b approaches infinity. Again, this is u to the minus 2. It integrates to u to the minus 1 over minus 1. You evaluate from 2 to the natural log of b. And as before, you get the limit as b approaches infinity of this thing that's going to infinity, to the minus 1 over minus 1, minus what you get at 2, which is plus a half. And as b goes to infinity, this goes to infinity, but you've got it raised to the minus 1, so this part goes to 0. This converges to a half, which means this converges by the integral test. So, if you were paying attention to what I just wrote, we were looking at this series. We used the integral test to decide whether this series converges or diverges. You change the discrete variable to a continuous variable. This function is always greater than or equal to 0, and it's decreasing and continuous, so we can apply the integral test. And at one step, if you're paying careful attention, I start to put 1 down here, and then I correct it and put a 2. But then when I made the substitution, when I had first talked about using 1 there, and I made the substitution, u equals the natural log of x, I said, oh, so that when this lower limit of integration is 1, u would be the natural log of 1. But then I changed, I realized that the lower limit of integration was supposed to be 2. But I never plugged the 2 into natural log. I never changed the limits of integration on u. When I do for b, but because I was correcting the 1 to a 2, somehow I never changed it on the 2. So instead of the natural log of 2 here, which I should have had, I just have a 2. And that mistake carries through. There should have been a natural log of 2 here instead of a 2. And here, after you've done the integral, it's still true the limit as b goes to infinity of this part is 0. But here, you'll see a half on the board in the original video. And it should have been 1 over the natural log of 2, and you get 1 over the natural log of 2. The conclusion is correct, that because this integral converges, this series converges. But you may wonder why I got a half instead of 1 over the natural log of 2, and that's because I made a mistake. Okay? Just be aware of that when you're looking at what's written on the board in the main video. So how useful is the integral test? Not too useful, because a lot of the series that we care about don't have nice integrals. We can't do the integral, or the series we care about involves factorials, and what do you do with that in an integral? But there's some integrals for which it's useful. But by far the biggest class of integrals for which, or the biggest class of series for which the integral tests are useful are given a name. They're called p-series. So we looked at the sum as k goes from 1 to infinity of 1 over k, the harmonic series. So we know this diverges. But just a minute ago, we looked at the sum as k goes from 1 to infinity of 1 over k squared, and we saw that that converges. And so what you might ask is, what if I just put an arbitrary exponent there? Can I decide when the series converges and when it diverges? So a series like this, the exponent is typically called p. This is called a p-series. This is a p-series, and we would say when p is 1, the p-series diverges. When p is 2, the p-series converges. The question is, can you say what happens for every p? And you can just do the integral test on 1 over x to the p. And what you'll find is what's usually referred to as the p-series test. It's easy. I'll just leave it as an exercise for you because all you do is the integral test. The p-series converges if and only if p is greater than 1. So if p is less than or equal to 1, the series diverges. So that includes equals 1. So yeah, that tells us why this converges and why this diverges and why this converges. You can immediately conclude, right, from this you can immediately conclude, oh, the sum is k goes from 1 to infinity of 1 over k to the 0.99. This diverges because 0.99 is less than 1, or less than or equal to 1, while if you just make the exponent a little bigger, sum as k goes from 1 to infinity of 1 over k to the 1.01, this converges. P-series are nice to have at our disposal. We use them all the time, and it's important to remember the P-series test. And here's the kind of bad news. We're going to have 4 different tests that have something special about the number 1 in them. In this test, it's a P-series, and the P belongs on the K in the denominator. We start with 1 over it. Don't think it's K to the P. You've got 1 over K to the P, and then where things change is that P equals 1. If P is greater than 1, the series converges. If P is less than or equal to 1, the series diverges. We're also going to have the limit comparison test, where 1 is what you expect to get for some limit. And then we're going to have the ratio test and the root test, where if you get 1 for the limit that's involved in the theorem, that's bad. The tests don't tell you anything. So it's important to keep all these 1s straight. In the P-series test, you want P to be greater than 1 for convergence. Another warning about P-series is people confuse P-series and geometric series all the time. Don't do this. So if you look, sum as k goes from 1 to infinity of 1 over 2 to the k, and you compare that, so versus the sum as k goes from 1 to infinity of 1 over k squared. Yes, these look similar. The denominators both have a k and a 2 in them, but in one the 2 is in the base, and the other one the 2 is in the exponent. Don't confuse these. Here, this is a geometric series. So this one is geometric. And it's another way that 1 comes in. Geometric series converge if and only if the r involved in the geometric series, the ratio of one term to the next, has absolute value less than 1. This is a geometric series. This, though, where the base is variable but the exponent is fixed, this is a p-series. It is important to keep these straight even though they look the same. This is a warning. People confuse those all the time. Don't be one of those people. All right. What we'd like to do now is look at some series that, I don't know, kind of look like p-series or geometric series. So we know about the convergence of geometric series. And we know now about the convergence of p-series. We also know about telescoping series, but really those are so special we won't use those. But what about some things that almost look like geometric series or almost look like p-series? Can we decide what those do? So let's look at, there were 2 examples that I really wanted. One's from the book. Let's look at the sum as k goes from 1 to infinity of 1 over k squared plus 3. And the sum as k goes from 2 to infinity of 1 over k minus 1. All right, suppose you look at these. Now, in fact, this one, if you look at it and you write out some terms, you'll see that this is the harmonic series. But we're going to kind of ignore that just to make a point. Because we want to think about the p series, 1 over k, where p is 1, and compare that with this one. The fact that this one starts at k equals 2 doesn't bother us. We know that leaving off a finite number of terms doesn't affect the convergence or the divergence of a series. So this one, it kind of looks like a p series where p is 2. Does that mean it converges? Maybe. This kind of looks like a p series where p is 1. Does that mean it diverges? Maybe. What's the big deal? Well, term for term, 1 over k squared is less than or equal to 1 over k squared plus 3 is less than 1 over k squared, because k squared plus 3 is bigger than k squared, so 1 over it's less than or equal to 1 over k squared. So term for term, this is true. And what does that tell you? Well, it tells you that as far as even the partial sums are concerned, now I'm writing this for the infinite series, but even as far as the partial sums, so the terms have this, satisfy this inequality. So certainly the partial sums do. And what you should think is, of course, or not what you should think, what's true, not just what you should think, is that it means that this is true, that this infinite sum is less than or equal to this infinite sum. But this one converges, which means this is some number, right? But this is less than or equal to that, which means that this infinite sum is bounded above. So really the partial sums are bounded above, which means this one converges, right? If this bigger one converges to something, like we know it's pi squared over 6, but that's unimportant. If we knew it was 57, then this can't get, right? There's only one way for a non-negative series to diverge. That's to positive infinity. If it's less than or equal to 57, it has to converge. And what it converges to is something less than or equal to 57. So yes, this one converges, and it converges by comparing it with this p series where p is 2. What we've just done is called the comparison test. It's a very simple test. It's, hey, if you're term for term less than or equal to something that gives you a convergent series, this is all for non-negative series, then the series has to converge. And there's nothing deep going on here except what I told you at the very beginning about non-negative series. They converge if and only if they're bounded above. They diverge only if they diverge to positive infinity. So once this is term for term less than that, then the partial sums obey the same inequality, and this infinite sum, so all the partial sums are bounded above by this infinite sum right here, and since this converges to something, this is bounded above, and so this has to converge. That's part of the comparison test. At the same time, yes, it's true, if you write out those terms, you'll see it's actually the harmonic series, but another way to look at it is that, 1 over k minus 1 is greater than or equal to 1 over k. We've made the denominator smaller, which makes the fraction bigger. So term for term, this is greater than or equal to that, which means that you should think this. The sum is k goes from 2 to infinity of 1 over k is less than or equal to the sum as k goes from 2 to infinity of 1 over k minus 1. But this one diverged to positive infinity, and this is greater than or equal to that. It diverges to positive infinity, right? So this diverges by the comparison test. This is all the comparison test says. It's not deep. in a sense it's deep, but it's not difficult to remember. For non-negative series, if you're term for term less than or equal to something that converges, you have to converge, and what you converge to is less than or equal to the one that's bigger than you. And if you're greater than or equal to something that diverges, well, it can only diverge to positive infinity, so for non-negative series. So you diverge to positive infinity. That's the comparison test. What tells you nothing is suppose we'd put a plus 1 here. If we'd put a plus 1 there, then 1 over k plus 1 is less than or equal to 1 over k. And this is so you put in the summations and you would think, oh, okay. Well, this one diverges because it's a p-series where p equals 1. In fact, it's a harmonic series. And this is less than or equal to that. That tells you nothing. In fact, this diverges because it itself is like part of the harmonic series, or essentially the harmonic series, but the actual comparison doesn't tell you anything. Knowing that this diverges tells you that this diverges to infinity, and all this says then is this number is less than or equal to infinity. Well, everything is. That has no content. This could be infinite, it could be finite, it would still be less than or equal to infinity. So being less than or equal to something that diverges doesn't tell you anything about this. And at the same time, being greater than or equal to something that converges doesn't tell you anything. If this had been a k squared minus 3, so that we had k squared, this denominator is smaller than this one, so this fraction is bigger. If, well, then we'd need to start somewhere else like it too. But then, yeah, it's true. You could conclude this, but so what? This converges. What does that tell you about this? It's greater than or equal to some number. Well, it could converge to a finite number greater than or equal to that, or it could go to infinity, which would be greater than or equal to that number. It tells you nothing. If you just think about these things, you don't have to memorize the test. If you're less than or equal to something that, what you need to remember is there's only one way for a non-negative series to diverge, and that's to positive infinity. So if you're less than or equal to something that converges, you have to converge because you can't go off to positive infinity. If you're greater than or equal to something that diverges, you have to diverge because you're greater than or equal to infinity. But being less than or equal to infinity tells you nothing. Being greater than or equal to something finite, being great doesn't tell you whether this converges or not. It does tell you that if it converges to something greater than or equal to this sum, but that's about it. All right, that's the comparison test. We would like to know that that this series converges. And even though it's greater than or equal, term for term, than this p series where p is 2. So let's look at this. You look at this and you think, well, it's true that this is greater than or equal, term for term, greater than or equal to the terms of the p series. It has 1 over k squared in it. So you're greater than or equal to something that converges. That doesn't tell you anything. The comparison test doesn't allow you to conclude anything. But what you should think is you look at this and you think, but when k is really big, this minus 3 is just negligible, and that series should do whatever, this series should do whatever this series does, and that series converges by the p series, because it's a p series where p is 2, which is greater than 1. So you suspect that this converges, just because when k is big, it looks like the p series where p is 2. Now, how do you make that rigorous that it looks like? And this is the more useful. This is typically more useful than the comparison test. It's called the limit comparison test. What it says, you compare two series. So just as in the comparison test, but it involves a limit. So suppose suppose you've got two series. So you've got AK is greater than or equal to 0 and BK is greater than or equal to 0 for K greater than or equal to some starting index. And suppose that the limit as K approaches infinity of AK over BK equals L, and L is unequal to 0 or infinity. Typically when we say a limit exists, we don't allow it to be infinity, but just in case that's a problem. So you've got, these are going to be the terms of a series. So you've got two sequences, what you should think of as terms, and you take the limit of their ratio and it approaches some limit L. You know, if the limit doesn't exist, you can't use this test. If the limit comes out to be 0 or infinity, well, if you're really careful, this test can tell you something in those cases, but those aren't the cases you typically care about. So I'll let you look up the more precise, or the more general statement in the book, but this is the typical case, and then the sum as K goes from M to infinity of the AKs converges if and only if. The sum as K goes from M to infinity of BK converges. So either they both diverge or they both converge. That's what it says. The proof of this, the idea of the proof, is not difficult. It's just if L comes out to be, say, a half, then it's like, oh, the AKs are eventually look like a half times the BKs. But multiplying a series by a non-zero constant doesn't change whether the series converges or diverges. So that's about all there is to it. Of course, there are technical details, but this is the limit comparison test. How do you use it? Well, you look at this and you think exactly how I said before. You look at this and you go, it's not a p-series, but when k is really big, it looks like the series 1 over k squared. The minus 3 should just be negligible. So I suspect that this does whatever the series 1 over k squared does. So you look at this and you think, when k is big, this looks like, so I'm going to put this in quotes, looks like this series when k is big. Now, what does looks like need to mean? It needs to mean the limit of the ratios exists and is something other than 0 or infinity. So exists and isn't 0. In fact, if looks like is correct, the L that you expect to get here is always 1. Right? The theorem tells you that if it comes out to be anything other than 0 or infinity, you can use this test. But what you expect it to come out to be is 1, because when you say that when k is big, this looks like this, what you should be meaning is the limit of the ratios, the ratio of the two things looks the two things look the same when kind of the same when k is big, which means their ratio should be 1, or getting closer and closer to 1 as k gets bigger. So what you expect in the limit comparison test is to get a 1 here. You don't have to, but it's what you expect. So what does limit comparison say? It says, okay, we see this series. We think when k is big, this series looks like this series. We know what this series does. It converges. So if we take the limit of the ratios of the terms of this to that, and we get a 1, or if we got 52, or 57 like I picked before, or the square root of pi, if we get anything, if the limit exists, isn't 0, then the two series do the same thing. We know that converges, so we would know this converges. Well, so you calculate it. You take the limit as k goes to infinity of 1 over k squared minus 3 over 1 over k squared. Or you could have taken the reciprocal. It doesn't matter. This is the limit as k goes to infinity of, you get k squared over k squared minus 3. If it's not clear to you what that does, divide the numerator and denominator by a k squared. This is the limit as k goes to infinity of 1 over, divide the denominator by k squared, 1 minus 3 over k squared. As k goes to infinity, 3 over k squared goes to 0, and you're left with 1. Yes, this limit is 1, which means by the limit comparison test, the two series do the same thing. And by the p-series test, this series converges, so that series converges. So if you're trying to write an explanation, like on a test or something, you would say that this series converges by limit comparison with this series, which, by the way, this doesn't start at k equals 1, but you still call it a p-series because, well, it's just 1 over k to the p. And we know that leaving off the first finite number of terms doesn't affect convergence or divergence, but which converges by the p-series test. Okay, so that's limit comparison. We could do a lot more examples, but that's how it goes. You look at the terms, you think, when k is big, this looks like, if I ignore these smaller parts, these things that should be negligible, this looks like something that I know. It looks like something I know about the convergence or divergence of. All right, I want to give you two more tests. They're very similar, the ratio test and the root test. In those tests, I'll say it again, it's important that you don't get 1. In the limit comparison test, you expect to get a limit of 1. The ratio test and the root test involve limits, and if the limit comes out to be 1, that means the test doesn't tell you anything, so that would be bad. Typically, it means you need to do something else. The root test is actually not used very often because it's harder to calculate. It's of theoretical importance. It applies to a kind of a broader class of series than the ratio test, and yet it's the ratio test that we use over and over again, and certainly what we used when we looked at power series and looked at their convergence. So we have looked at the ratio test before in the context of when we were looking at power series, but the ratio and root test. So the ratio test. Let me state the ratio test, and then I'll change it. I'll kind of erase some parts of it. So once again, suppose you've got a non-negative series. Suppose bk is greater than or equal to 0 for k greater than or equal to m. Suppose and suppose that the limit as k approaches infinity. In fact, this looks kind of like a limit comparison test, except you're comparing the series with itself. So it's not that. So, and suppose that this equals L. So this limit exists. It equals some number L. Then, and you should remember this from when we talked about it during power series, then if L is less than 1, the sum of the bk's converges. And this isn't particularly difficult. This limit being L means that each next term, b sub k plus 1, is practically L times b sub k. So it's like you go from one term to the next by multiplying by L. So it's as though you've got a geometric series where the thing you multiply by each time, which we normally call L, R, is this L. But if you had a geometric series with the R less than 1, you'd know it converged. Well, this looks like that when k is big, because b sub k plus 1 is approximately L times bk. And if L is less than 1, then it looks like a geometric series where R is less than 1, and you would expect convergence. 2, if L is greater than 1, the sum of the bk's diverges. In fact, that means that the series fails the term test for divergence. Because the terms are getting bigger as you go out, because bk plus 1 is approximately L times bk, but L is greater than 1, so your terms are getting bigger, so they're not approaching 0. Unless they were 0 a bunch of times, and then this quotient's not defined, so the limit doesn't exist, so that can't be happening if you had the limit. And finally, if L equals 1, we usually say the test fails, and what we mean by that is you can't conclude anything. That if you apply the ratio test and the limit comes out to be 1, then maybe the series converges, maybe it diverges. There are examples of either one. All p-series, if you take a p-series, I'll leave it as an exercise, but for any p-series, the ratio test will give you 1. So the ratio test is useless for deciding on the convergence or divergence of p-series. That's why we had the integral test. So this is the ratio test. It's pretty much exclusively what we used when we looked at convergence of power series and found their radii of convergence. Let me do some examples before I change this and make it the root test. In fact, I'm not really planning to give any examples of the root test because it's more difficult and it doesn't really come up in many examples, or it doesn't. In most of the examples where you'd want to use the root test, the ratio test is easier. So examples, I want to look at 3. I want to look at the sum as k goes from, I really don't care where I start these series. It's, the convergence or divergence isn't affected by leaving off the first finite number of terms. So sometimes we just omit those where k is starting. We know it goes to infinity. We omit where k is starting and just assume it starts somewhere big enough so that everything's defined. I want to look at these 3 series. All right. I want to look at these 3. Okay. When you see a factorial in your series as part of your terms, it's kind of a dead giveaway that you'd like to use the ratio test. I remind you of what I've reminded you of before, that k plus 1 factorial is k plus 1 times k factorial. So that k plus 1 factorial divided by k factorial is k plus 1, or the other way around, k factorial divided by k plus 1 factorial is 1 over k plus 1. So if you apply the ratio test, here you would look at the limit as k approaches infinity of the k plus first term. That means you replace each k with the quantity k plus 1. So you get k plus 1 factorial over 5 to the k plus 1 divided by k factorial divided by 5 to the k. You invert, multiply, and collect the things that look similar. You get the limit as k goes to infinity of 5 to the k over 5 to the k plus 1 times k plus 1 factorial divided by k factorial. So we get this. This is a fifth. This is k plus 1. So we get the limit as k goes to infinity of 1/5 times k plus 1. This is infinity. And I should have said that in the test. In fact, suppose that where L is, we allow infinity here, where L is an extended real number. So that all that means is it's allowed to be plus or minus infinity. All our terms are non-negative. It can't be minus. So we're allowing for the possibility that it's infinity. That's kind of a stunningly bad case of number 2, that if L is greater than 1, the series diverges. Well, L is coming out to be infinity. Infinity is greater than 1, so the series diverges. So that's what we're concluding right here. This diverges by the ratio test. Right? The L came out to be infinity, and I'm glad we did this example because I should have emphasized that L could be infinite over there, and we'd still, and you know, the series diverges. All right, what about this one? To handle that one, you need to take by the ratio test. Why would you think of this as the ratio test? I told you every p-series gives you a ratio of 1, and that looks kind of p-ish. You know, it's k to the some power. As a p-series, the p would actually be negative 1,000 because you need 1 over k to the p. But that part looks like p-series, but this part looks like geometric series. So we're going to do the ratio test anyway and see that the geometric part, this part will give us a 1 in the limit, but this one won't. It'll give us a 1.01 in the limit, and we'll see what happens. So you take the limit as k approaches infinity. The kth plus first term. So you replace both k's by the quantity k plus 1 to the 1,000 over 1.01 to the k plus 1. And you divide by the kth term, which is k to the 1,000 over 1.01 to the k. You invert, you multiply, you collect similar looking things, and you get the limit as k goes to infinity of, you get k plus 1 to the 1,000 divided by k to the 1,000. That's k plus 1 divided by k to the 1,000th power. And then you invert and you multiply, you get 1.01 to the k divided by maybe I'll write it. You get 1.01 to the k divided by 1.01 to the k plus 1. All right, as k goes to infinity, this is, you can rewrite k plus 1 over k as 1 plus 1 over k. As k goes to infinity, this goes to 0 and you get 1 to the 1,000th. That part goes to 1. This part, as well, you can just divide. This is just the same as 1 over 1.01. So as k goes to infinity, this part goes to 1, and you're left with 1 over 1.01. Well, that's less than 1. So this converges by the ratio test. Right? If the L in the ratio test comes out less than 1, the series converges. If it equals 1, the test doesn't tell you anything. If it's greater than 1, it diverges. That converges. It's part of what you're supposed to look at in this example is, wow, this k to the 1,000th power looks really big when, like when k is 2. Up here you have 2 to the 1,000th power, and down here you just have 1.01 squared. So the numerator looks much bigger than the denominator for small k. Well, not when k is 0, but when k is 2 and bigger, 2, 3, 4, even when k is relatively small, other than 0, 1, this numerator is much bigger than the denominator. So you might think, oh, this diverges because the terms are big. They're not approaching 0. But yeah, no, it converges because what we get from the ratio test is less than 1. So that converges. Finally, I'd like to look at this one. This one is a mess, but we can do it with the ratio test. You just have to be clever and you have to remember one particular limit. So let me rewrite this integral. The sum, as k goes from 1 to infinity, of 7 to the k times k plus 1 over k to the k. All right. What does this series do? Well, these are supposed to be examples of using the ratio test, so we're going to use the ratio test. In general, though, if we weren't giving examples of the ratio test, we were just giving series, you have to be able to look at a series and know which of your tests to use. There's no substitute for practice. You practice these enough, things get pretty clear. All right, let's try the ratio test. In the ratio test, the limit that we're after would be the limit as k goes to infinity of, all right, the kth plus first term. So this, with all the k's replaced by the quantity, k plus 1. So we get 7 to the k plus 1 times k plus 2 divided by k plus 1 to the k plus 1. And now this is divided by the kth term, which is 7 to the k times k plus 1 over k to the k. All right. So this is what you have to do. You invert, multiply, collect things that look similar, and then we have to get a little clever. You take the limit as k approaches infinity. We will get 7 to the k plus 1 over 7 to the k. Well, that part's easy. That's 7. All right. So that's that and that. We'll get a k plus 2 divided by a k plus 1. Okay, that goes to 1. So that's easy to handle. But then we get this nasty thing, this k to the k over k plus 1 to k plus 1. Now, all right, this is 7 on the nose. It doesn't matter what k is. This limit approaches 1. So what we're getting is 7 times 1 times whatever this limit is. So we need to handle the k to the k over k plus 1 to the k plus 1. This might look a little unmanageable, but write k plus 1 to the k plus 1 as k plus 1 to the k times another k plus 1, right? We had k plus 1 to the k plus 1, so yeah, this is the same thing. You would add the exponents. Why do that? Well, now you can at least lump these together as something to the k. Maybe that'll be helpful. It'll turn out that it will be, but maybe that's not clear ahead of time. So we have 7. Don't let me forget that part. 7 times the limit as k goes to infinity of k over k plus 1 to the k times 1 over k plus 1. All right, this part's going to 0, and you might think, well, then it doesn't matter what this does. That part goes 0, so the whole thing goes to 0. Well, it does matter. If this part went to infinity, then, just something that looks like infinity times 0, well, then you'd have to do more work. We need to analyze this limit right here, and let me do that as kind of a side problem up here. In fact, let me look at the limit of that upside down, and then that limit will be the reciprocal of what I'm about to write. So the reciprocal of that is k plus 1 over k to the k. This is the limit as k approaches infinity of 1 plus 1 over k to the k. Now, here's the good news, bad news. How do you figure out what this does? Well, you could take the natural log and use L'Hopital's rule, but you're just supposed to know this limit. Now, you may not remember this limit, but you're supposed to know it. If you put k equals 1,000 in your calculator and take 1 plus 1 over 1,000 raised to the 1,000th, I suspect you'll recognize what you get. But you really should remember, this is e. That is e. But this was the reciprocal of this. So this is 1 over e. So we're getting 7 times 1 over e times, well, 0. So that's 0. 0 is less than 1. So this converges by the ratio test. Because we got L is 0. You know, it's not true that all the, you know, it's not normal in ratio test problems and examples that you get some limit that's really hard or that you're supposed to have memorized, but it's not hard to come up with those kinds of examples, but we don't throw many of those out there. All right, that's all the examples I want to do on the ratio test. Let me state the root test for you and then tell you that we're not really ever going to use it, and I'm not planning to do any examples for it. The root test is of theoretical importance, and what it says is instead of the ratios, you have the kth root of b to the k. You take the kth root. Now, this, of course, is why it's called the root test. And then you call the limit L, where L could be an extreme real number, and the conclusions are the same from the ratio test. If L is less than 1, the series converges. And again, it's because it looks like a geometric series. If you say that this limit is L, well, then when k is big, what it means is b to the k is approximately L to the k, right? If you raise both sides to the k, saying that when k is big, this is approximately this, also means when k is big, b to the k is approximately L to the k, which means it looks like a geometric series where R, once again, is the L. And if it's less than 1, it looks like a geometric series where R is less than 1, so it converges. And if the R is greater than 1, so L is greater than 1, it diverges. And if L equals 1, the test doesn't tell you anything because it's a question of kind of how it approached 1 through bigger numbers or smaller numbers. And that's the root test. It's you can use it in certainly, okay, I said I wouldn't do any examples, but although it's not like you should have to use it here, but if you wanted to use it on a series like this, well, certainly you would. I mean, the ratio test here wouldn't be particularly nice. Of course, those terms, you could compare this with like 1 over k squared, and this is smaller than that. But if you want to use the root test, certainly the root test would be easy here. You take the limit as k goes to infinity of the kth root of the kth term. Well, that's the limit as k goes to infinity of 1 over k, which is 0, which is less than 1, so this certainly converges. But aside from something that's terms that are explicitly raised to the kth power, the root test tends to be a lot harder to use than the ratio test. All right, those are a lot of tests, and you get to mix them up and use them and use more than one of them sometimes in different problems. They're not too bad as long as you keep all the stuff about 1 straight. A p series where p is greater than 1 converges. If you get a 1 in the ratio test or the root test, that's bad. The tests don't tell you anything. And a 1 is what you expect to get for the limit and the limit comparison test. So try to keep all that straight. In the next and last section, what we're going to do is look at series with both positive and negative terms and see what kind of weird things can happen there.